Hello everyone, my name is Yunus, and welcome to my very first YouTube video on the journey to becoming a design verification engineer. This video is especially for students in electrical and computer engineering. Today, we're starting from the basics, exploring logic gates and diving into the fundamentals of SystemVerilog. But before we get into the coding, I want to take a moment to explain what Verilog is and how we can use it to verify our designs. Verilog is a powerful hardware description language that allows us to model digital circuits and ensure they work as intended. I'll also be sharing a few helpful links throughout the video so you can deepen your understanding of Verilog and follow along with its evolution in the industry. We're going to unlock the full potential of SystemVerilog, learning everything from basic gates to verifying our very own designs so that you can excel as a verification engineer. On the design side, you'll discover key features such as interfaces, essential for encapsulating communication and performing protocol checks. Enhanced data types, beyond the basics, you'll work with C-like data types, like int, user-defined and enumerated types, typecasting, and even structures and unions. Packages, learn how to use packages to share definitions across multiple design blocks efficiently. On the verification side, SystemVerilog empowers you with powerful tools like advanced data types, strings, dynamic arrays, associative arrays, and queues that make testbench development more robust. Object-oriented programming, harness the power of classes for creating flexible test benches. Constrained random generation, automate the creation of diverse test scenarios. Assertions and coverage, ensure your design meets specifications and thoroughly validate functionality. Synchronization techniques, critical for managing interactions between different parts of your test environment. To write code and verify the design we need, industry tools and vendors. While the market features robust tools such as Mentor Graphics, with the Questa simulator and precision RTL synthesis. Synopsys, offering the VCS simulator, DC Ultra, and Simplify Pro synthesis. Cadence, with its incisive simulator and Genus RTL synthesis. Intel, formerly Altera using Quartus. Xilinx, leveraging Vivado. For our learning experience, we'll be using EDA Playground, a fantastic, web-based platform that lets you write, simulate, and test SystemVerilog code directly in your browser. It's perfect for both beginners and seasoned engineers who want to practice and refine their skills without installing heavy software. So, buckle up and join me as we dive deep into SystemVerilog on EDA Playground, mastering both design and verification from the ground up. In the industry, there are two primary types of modeling. Combinational logic modeling, where outputs depend solely on the current inputs, and sequential logic modeling, where outputs depend on both current inputs and past states. Today, we're focusing on combinational logic modeling by designing a simple two-input and gate along with its test bench. Getting started on EDA Playground. Open EDA Playground and create an account. After creating an account in EDA Playground, on the left panel, under Languages and Libraries, select SystemVerilog. Next, choose your preferred simulation tool from the options, Cadence, Synopsys, or Siemens. I personally select Cadence and then set the Run option to Show Output File after Run. Once you're set up, you'll notice the screen is divided into two main areas, one for your design code and another for your test bench code. Before going to code, here is AND gate and its truth table. Now, we are designing code for the AND gate in behavioral modeling. First we have module declaration. The module is named N_gate and it has two input ports, A and B, and one output port, Y. All ports are declared with the logic type, which is commonly used in SystemVerilog. Second we have always_COM block. The always_COM block is used to describe combinational logic. This block automatically re-evaluates whenever any of its input signals, A or B, change. It's similar to the always at asterisk block in Verilog but with additional checks to ensure it only describes combinational logic. Then we have if conditional statement. Inside the always underscore comb block, an if statement checks the condition, A and B. If both inputs A and B are true, logic high, the output Y is set to 1 foot B1, binary 1. Otherwise, Y is set to 1 foot B0, binary 0. End module. This keyword marks the end of the module definition. This code snippet models a 2-input and gate in a behavioral style, making it straightforward and easy to understand for verifying your design. In our next segment, we'll create a test bench to simulate and verify that this AND gate operates as expected. Now we are going to write code for our design called as test bench. First module declaration. The test bench is declared as tb_n_gate. This module doesn't have any ports because it's a self-contained simulation environment. Second signal declaration. 3 signals are declared using the logic data type. A and B, these represent the inputs to the AND gate. Y, this represents the output from the AND gate. Device under test, DUT, instantiation. The AND gate design, our AND_gate_behave module, is instantiated with the instance name .. The port connections are made using named association, .a, etc., linking the test bench signals, A, B, Y, to the corresponding ports of the DUT. Stimulus application. An initial block is used to apply a sequence of test vectors. $monitor statement. This command continuously prints the simulation time, $time, and the current values of A, B, and Y whenever any of these signals change. Test vectors. The input signals A and B are assigned different combinations. First, both A and B are set to 0. Then, A is 0 and B is 1. Next, A is 1 and B is 0. Finally, both A and B are set to 1. Each assignment is followed by a number 10, delay, which pauses the simulation for 10 time units before applying the next set of values. $finish. Once all test cases are applied, $finish terminates the simulation. This test bench effectively drives the AND gate design through all possible input combinations, allowing you to verify that the output Y behaves as expected. Feel free to run this code on EDA Playground to see the simulation in action. And in second style uses a continuous assignment to directly express the AND operation. That's why it is called data flow modeling or combinational modeling. Since the interface, the list of inputs and outputs, of the AND_gate module remains unchanged, there is no need to modify the test bench even though the internal modeling style of the design has changed. In other words, if there is change in netlist in design, we have to change netlist in test bench also. The combinational modeling style code for AND gate is as follows. First we declare the module and end module. The module is named AND_gate and defines 2 inputs, A and B, and 1 output, Y, all of type logic. Continuous assignment. The statement assign Y equals A and B continuously drives the output Y with the result of the bitwise AND operation on inputs A and B. Since this is a combinational, or data flow, modeling style, the logic is expressed directly through this continuous assignment rather than using procedural blocks, like always_comb. Data flow modeling. This style clearly illustrates the flow of data. The output Y is always updated to reflect the current values of A and B. It is called data flow modeling because it represents the computation as a direct flow from inputs to outputs, which is ideal for simple combinational logic. This approach is concise and efficient for modeling simple combinational circuits like AND and gate. I hope you've enjoyed this first step on your journey to becoming a verification engineer. For more details, please check out the link in the description. In our next video, we'll dive into sequential logic design and its test bench. Thanks for watching, and I'll see you next time, signing off.